All right, got the recording on. All right, we're going to wait for, Ed's here. Ed is here. He's tuning in right now. So after Ed speaks, we'll talk about field day.
I hear you guys? Yeah.
Hello.
Hello, I can hear you guys. Can you hear me?
Yeah.
Jim, you should read one of those.
Hey, Jim. Oh, here. There. There you go. Now you can see me. See, I don't hear your audio. Oh, hang on. USB here. Oh, okay. Hey, Jim, I don't hear your audio.
All right, can you hear me now?
Yeah. Now I can hear you. Yes, loud and clear.
All right. Thank you. Our guest tonight, we're going to have an echo. Our guest tonight is Ed Fong, WB6IQN. As many of you know, he was the inventor of the DBJ-1 and the DBJ-2 antenna that was featured in the February 2003 and March 2007 QST. His latest articles in QST was a DBJ-1, a triband antenna published in March 2017, and the DBJ-2 won the Plaque of the Month award. There are over 30,000 of these antennas in use today, about half used by house and the other half used by government commercial entities. And in his presentation, he will review how the original DBJ-1 works and then how he managed to convert the original DBJ-1 into a portable antenna. He was first licensed in 1968 as WN6IQN, and he later upgraded to extra class. He has a real extra class license, by the way, because that was when you had a 20 words per minute of CW to pass. With his present call WB6IQN, he obtained BSEE and MSEE degrees from the University of California, Berkeley, and his PhD from the University of San Francisco. A senior life member of IEEE, he has 12 patents and over 40 published papers and books in the area of communications and integrated circuit design. Presently, he's employed by the University of California, Santa Cruz, previously with Berkeley 1997 through 2010, as an instructor teaching graduate classes in RF design and high-speed interface. In his 35 years, he has done work for Stanford University, National Semiconductor, Advanced Micro Devices, and numerous startup companies in Silicon Valley. Can we all please welcome Dr. Ed Fong?
Hey, move the camera computer so I can see the audience. It's not aiming at the audience.
What?
You see, the camera from their laptop is pointing at the lights. Ah, there you go. There you go.
Better?
Much better. Much better. Hey, so were you going to run the meeting first, Jim?
Say again?
You said don't you guys run a meeting first, or do you want me to go ahead?
No, we're ready for you.
Oh, okay. Okay. Oh, good. Okay. Oh, fantastic. Oh, thank you, Jim. So, hey, how hot was it up there today?
Yeah. Hot.
Yeah, it's hot down here. It's in the hundreds. Oh, no, today it's cooled off. 90. Yesterday it got up in the hundreds. Today it was like 95. Now it's cooled off. So you see my room here. I've got all the windows and everything open. Because we don't have air conditioning down here. When these homes were built here, it was before global warming 50 years ago, and a few hot days. Now it's June. It's like this already. Pretty bad. Okay, I'm going to share a screen. Okay, I'm going to do a share screen. Okay, you have to, okay, ready? Host disable participants share screen. Okay. Hang on. Okay, Jim, you got to do something to let me take control of the share screen. What do you have to do? It's something like you have to let me take control. Let me try this again. Host this out. No.
Try it now.
Oh, I hear your audio. Okay, let me try it now. Aha, you got it. You got it. And I got to find which screen. Now, I got this. So where's my, it's that one here. There. I think.
All right, we got it.
Then I got to do something like this, like that. Ta-da, you got it right? You see that?
Yes.
Yes.
Okay, great. Okay, fantastic. Then we're ready to begin. And what else do I need here? I think for the time being, let me get something to drink here. Let me get my nano. Hang on. Here. Okay. Thank you very much. You guys are right up north, about 4 hours north of me. Yeah, it was hot today. It's finally, I think it's going to cool off. It's going to cool off by tomorrow. All right. Anyway, thanks for the introduction there. Yeah, tonight we're going to talk about, and maybe I can't see. Yeah, I guess if someone raised their hands, I could see it on the screen there. You can kind of interrupt me if it's important. Try to write a note for it and save it for the end. It might be a little easier the way it's set up, because I could see you guys, but kind of small. Wow, there. Oh, so you have two cameras. That's pretty cool. One's really sharp. All right, let's get going. Anyway, thanks for the introduction, Jim, and thanks for inviting me. Yeah, I'm glad COVID's over, and we're going to start meeting again down here pretty soon too. We haven't had meetings for over a year. So what I'm going to talk about tonight is how we basically made a single band J-pole, which was pretty popular, into a dual band J-pole without compromising the performance. So quick question, just I can see the whole audience. How many of you folks have one of our antennas? Oh, that's good. Oh, one? That's good. I can sell you a bunch. This is how we raise funds to my group at UC Santa Cruz. And we sell quite a few of these, but that's how we raise our funds, going to ham. I do all the talking, go to ham clubs, but we have a few contracts with FEMA, a few contracts with some agencies, ATD alarm systems. But yeah, we always use the ham community for help in field days coming up next week. We're not going to get together formally because of COVID, but I'm going to go up the hills here and do some work. So anyway, let's continue with this. What I'm going to talk about tonight is the antennas we developed about 15 years ago originally, and we've done subsequent improvements to it. Again, basically trying to make a single band J-pole, which a lot of you guys are familiar with. How do you make a dual band? Simple, you got to make it simple, reproducible, economical. How do you do that? So some of this was featured. Our original article was published way back in 2003. Then we did a roll-up version in 2007. And our most recent one is 2017. We did a triband, how you make a triband, 2 meters, 220, and 440. So let's move on here. So here's kind of the articles that appear in QST. This is the original one here. This is the one in the roll-up that one of my students suggested. This is, can you ever make a roll-up out of and make a dual band? That'll be pretty cool for backpacking. So we did that. And then our latest one is the triband one that's become very popular. It'll do 2 meters, 220, and 440, all in one antenna here. It's a little shorter now. We managed to make it a little shorter. It's only about 5.5 feet tall now. That's my daughter, KJ6QXM. Holding next to it, she's got her master's in mechanical engineering and also a certificate in electrical engineering and a bachelor's in mechanical engineering and a minor in math. So she does okay. So she helps me out every now and then. She's over at Boise State now. And then we also had to patent some of this stuff. Not that we wanted to. I had no concept of patents. Things that, usually we patent the stuff at the university, more academic stuff. But we found out when we did the first one, the DBJ-1, the one that I'm going to cover today, back in 2005 or so, people started copying it. And it kind of bothered me, but I said, well, the copying is the best flattery, right? If the copying must be pretty good. So I figured it didn't bother me. Then I started seeing my antennas being sold on the internet on eBay. And that made me a little uncomfortable. But the thing that really drew the straw was we started buying them. I had a couple of students, because I couldn't use my name. I had a couple of students, I go purchase these. Let's take a look at these. Not a single one. And we had about 3 or 4 copycats out there. Not a single one even came close to our spec. That's bad. That's really bad because they start using your name. Here's the Ed Fong antenna. No, it's not the Ed Fong antenna. You didn't make it right. You didn't understand it. You just took the dimensions. And it's, as you'll know by today, it's more than just the dimensions. It's the wavelengths and the velocity factors that make it actually work. So that's when the attorney at the school says, you got to patent some of this stuff. I mean, as simple as you think it is, if people are copying it, it's not that simple. So Mike Kaufman, the attorney, started writing up patents for us. And also, we couldn't patent our original antenna. It was too late. If you ever read our eBay ad, he wrote that eBay ad. He said, well, then the only thing to do is write your ad like this. Don't buy from copycats. Buy from the original inventor and all this. And that worked. By the way, that got rid of all the copycats. We don't see those anymore. So here's our patent on our triband. I give another lecture on how do you get gain out of a J-pole antenna. It turns out it's not that simple. You have to make it into a collinear, which is a little bit more complex. And you hear all these people saying, oh, get 6 dB gain out of this J-pole. I haven't seen any of them like that yet. It's a little bit more complex than that. The triband one's kind of interesting. So I give a talk on the triband. We give a talk on how to get gain and the theory behind how to get gain out of an antenna. And then we have a DMR talk. And by the way, I'm also working on one. You guys probably come on down to PacificCon. I might be giving a talk on the nano VNA, how to actually use it for various applications. Here it is right here. You can't beat one of these, $60, right? Raise your hands. Who's got one of these? No one? You guys got to buy one. I don't sell them, but boy, for $50-$60, you can't beat it. Oh, one, yeah. You can't beat it. It's a full network analyzer. You can't beat it for the money. Because we use a 5062 in our lab here, and that's a little under $50,000. But I think for under 2 or 3 gigs, this one works fine. It doesn't have quite the dynamic range of it, but it's great. I mean, I use this all the time to test out things. I do not use our big one because it's too big. You get a lug it. Here, it's portable. You just bring it to the spot you want to measure it, take your measurement, and it's done. Battery operated. You can't beat it. So you guys should get 150. I mean, If you know how to use it, it's an antenna analyzer. It's a network analyzer. You can tune filters with it. You can tune duplexers with it. And the one for $60 is good up to 1.5 gigs. So I hate to say this, that pretty much obsoletes all these, just the antenna analyzers, because that's a network analyzer. Okay, so let's start our talk here with the antenna. Why did I choose a J-pole to try to make a dual band? I like the J-pole configuration because it doesn't have radios. So it's no radios. Ground plane, with the radios stuff, has a lot of wind load. It starts blowing down. I had a bunch of ground planes I was growing up. That's how we built antennas back then. 2 meters. 2 meters you could do a ground plane. UHF can do a ground plane. But I found that they didn't last that long. And then I bought some Ringo Rangers with ground radios, and they broke off eventually. But a J-pole actually comes very close to a vertical ideal dipole pattern. A ground plane does not. A ground plane is distorted because it's not symmetric. And what you find is the J-pole actually gives you about 1.5 dB more gain. And we'll get into this why. I mean, that's not significant, but it's probably noticeable on a weak signal. It's also end-fed. I like this idea it's end-fed. We'll get into that, as opposed to being center-fed like a dipole. See, so here's a photo of Mount Sutro. If you guys have driven down the city, I'm sure most of you guys have. That's one of the main tower on Mount Sutro. Aside from the big tower, this is the side tower. But if you look at this, I took this about 3 years ago. There's not a single antenna here with ground radios anymore. I can't find one. There might be one, but I can't find a single one that has ground radios. If you had taken the same picture 20, 30 years ago, most antennas would have ground radios. But when you have ground radios, that implies a ground plane antenna. A ground plane antenna, I'm sure a lot of you guys have built them, is an open circuit, open DC circuit, right? It's a center radiator with radials. And if you ohmed it out, it's an open circuit, which means it can collect charge, which means you need a lightning arrestor. We'll show you with the J-pole. You don't need that. You design it out. You literally design it out. So you do not need lightning arresters with J-pole type configurations. So I like that J-pole. So that's why let's take the J-pole and let's see if we can dual band it. See, here's a dipole. Here's a vertical dipole, very well constructed one out of copper, and it's soldered on and all this stuff. But you notice its arm has got to come out because you got to center feed it. A dipole center fed. It's not end fed, which means it has to come out in the arm. The example I always give is, do I have a broomstick here? I usually try to think here. I'll find a broomstick. Okay, well, how about just a PVC pipe? I'll give you a quick example of why you don't like this design. It does not hold up over time unless it's very, very well made. Because like here, if you hold something vertically, it's easy. If you're a mechanical engineer, you can figure out all the forces. So if you can get an antenna vertical like this, it's easy to hold up, which means it has good wind load or good wind resistance. But if you got to stick anything out horizontally where the gravity now pulls it down in what's called R cross F, try to hold it up like that. Now that's much harder to do. So anything that sticks out like that puts a lot of stress at this point. R cross F, it keeps on over time. It'll bend, and eventually break. And if you just solder this end, what you'll find is solder is not that durable. It will break eventually. You got to really do this out of steel with threads. Then it holds up, but then that gets very expensive, very tedious. So you want to get away from a design that produces torque. In this case, torque is right there. R cross the force F. That's the torque that it produces. You don't produce torque when you hold up a vertical element because the distance is 0, R cross F. The R is 0. So you just have to kind of mechanically engineer this stuff out. Okay, so I first saw the J-pole. Again, I grew up with ground planes and dipoles back in the 60s and 70s. But when I saw this about 1990, I thought, I played around with it. My friend Denny Monticelli, AE6C, introduced me to it. And I tried it. I said, I like this configuration. That's pretty cool. The only disadvantage of it is that it's half wavelength, and then you need another quarter wavelength to match it. And I'll explain how it works. And we've delivered yet, let's say that's an obsolete slide. We over 30,000. I've kind of lost track. It's over 30,000. So I felt that this J-pole design, and I'm sure a lot of you folks use J-pole, copper J or ribbon J or whatever. It's a very good design. And actually the concept of it came up in the 1930s, but hams just started applying it by the 1990s, 2000. And now most antennas are that configuration. And I think a lot of it, commercially they do it because you don't need a lightning arrestor. It's a DC shorted antenna. So for the price and the performance and the durability, the way it holds up instead of torquing, it's great. But what's interesting is a standard one won't do dual band, of course. That's where this issue came up in about year 2000. They go to these swap meets. I'm sure you guys have swap meets up there. I heard you guys had a good one. Well, it's not that close to up in Sacramento. A friend of mine went to one in Sacramento, what, 2 weeks ago? I thought it was fantastic. And we're going to start them up again here. I'm on the board because we just got to find a spot. And I think everything's cleared. We used to have it at Fry's Electronics, but they went broke, so we can't use their parking lot anymore. I got to find another place. Anyway, so by the 2000 era, all these handy talkies were coming out, dual band, and mobiles too. They were dual band. People weren't buying single band radios anymore because the UHF repeaters were coming up. The UHF repeaters were coming up because the VHF channels were all taken up. Now the VHF and UHF channels are taken up. 220. In fact, in the Bay Area here, all the 220 slots are even all gone. So what the folks wanted to do is by the year 2000, hey, how do I get a good antenna? I just bought myself a dual band handy talkie. Well, they found that the old 2-meter one kind of resonated at UHF. At least when they put a watt meter on it, or SWR meter on it, it was okay, not great, but okay, 1.5 to 1 or so. Won't blow out the radio. But what they found quickly was that it doesn't work very well. In fact, it gives about, if you actually simulate it or work out the equations, it'll do 6 to 8 dB less than a ground plane at UHF. Why? Because, I'll show you a picture. Because if you actually simulated this thing on like EasyNAC or ADS or HFSS on this simulation software in free space, we'll just reference it to free space, not distort it with different grounds, but just reference it, pretend you're in free space. It's a good way to compare things. Well, in free space, a vertical dipole at its fundamental gives a pattern like this. Figure 8, right? This is the sky is up here, the earth is down here, and sea level is right here. And so typically you'll be transmitting here and the guy you're talking to is right over there. So the fundamental of vertical dipole looks like this. It's a pretty decent pattern. Again, if you look at it from the sky, the coverage is 360 degrees. And it's really good because a lot of the energy doesn't go up into the sky. You don't want it to go up in the sky. You want it to go on Earth. So it's a pretty good pattern. Now, if you use it on its third harmonic, which is UHF, and again, on UHF, the matching's okay. But if you simulate this pattern in free space, what you find is that the lobes look like this. It's no longer this figure 8 pattern. It looks like a 4-leaf clover. Well, that kind of presents a problem. Here's the sky. Here's the earth. You're standing here. The guy talking, all the signals going up at 45 degrees. That's not good. And if you actually quantify it, it's about 75%. 6 dB is about 75%. That's a 75% of it's going in the sky. Or what you HF guys, what you call, hey, what you got, a cloud warmer there? Oh, this is an ideal cloud warmer. So you don't want that. So again, only about 25% of it actually at UHF goes to at sea level. So you're all of a sudden your 4-watt walkie-talkies, you're going the wrong way. Now it's looking like a 1-watt walkie-talkie. You want to have gain. So we have to solve that. That's the main problem. Okay, so how do you solve that? The first thing you got to do is you got to look at a Smith chart. If you guys don't understand Smith charts, if you're playing with radios, you don't have to, but if you're doing with antennas and things like that, and by the way, this network analyzer gives you full Smith chart capabilities, which is amazing. It gives you, antenna analysis, network analysis, which will give you a Smith chart. But the only thing you need to know here in this talk is, and there's a lot to learn in the Smith chart. We offer our high-speed I/O classes, 40–50% based on how to use the Smith chart. So I'm not going to teach you everything about the Smith chart today. It takes years just to learn little things about it. I don't know everything about it. I know the things that are relevant to me. That's about it. But the thing we're going to talk about tonight is what's relevant here is in a Smith chart, what it says is if you start out with a short circuit on a transmission line. If you short circuit one end, if you go a quarter wavelength, it will read an open circuit. That's AC. Now, most of the new grad students, this is how I know when a grad student is a ham or getting into wireless RF because they see that there's jobs out there and I want to get a master's in it. If you ask this question, the first day in class, the ones that get it are usually hams. Because let me get a quarter wave stub here. I've got a bunch. Hang on. Quarter wave stub. Quarter wave stub would be right here. I do. Here you go. So here's a quarter wave stub. That's about five inches or so. So 5 inches UHF quarter wave stub. And you old timers here, you guys probably use quarter wave coaxes all the time to tune things, you bring things down, bring things up, trim it. Because it says if I short this end, short circuit, a DC short, at UHF, go up quarter wave, which is about 5.5 inches. That means you can go around the Smith chart 180 degrees. That's a quarter wave. It's going to be an open circuit. Now, that's at UHFs. So if you're taking a UHF measurements at 445 megahertz, for example, it's going to be high impedance. And vice versa, if you leave it open circuit the bottom, and if you put a network analyzer here at about 445 megahertz or so, it'll read a short circuit. People found that rather amusing, but I think most engineers are not. That's how waves work, because we think in terms of DC. If it were DC, if you short it here, obviously it's short here, if it's open here, it's open, that's DC. We're not talking DC, we're talking about waves. So you have to kind of look at it from a Smith chart point of view. So that's really important. Really important to keep in mind that if you short circuit one end, a quarter wave later at that particular frequency, it will be an open circuit. And if it's an open circuit, it will be a short circuit. And you can use that as a filter because that's only narrow band. This is only a quarter wavelength at one frequency, about 445 or so. Basically, it makes a filter. And I've actually played around with it. You hams have probably, if you're old timers, you've probably played around with quarter wave stubs to get rid of harmonics and things like that. Because in a harmonic, all you do is open circuit. If you want to get rid of a harmonic, it's an open circuit here. Quarter wave later, for the harmonic you want to get rid of, it's a short circuit, and you tee it right in your coax. And it's an ARRL handbook. They show you how to do it. Okay, so let's go to the J-pole. Exactly what it does. I'll explain how it works. Very clever design. I didn't design it, but the concept, since the 1930s actually. They used to call them ZEP antennas. But the way it works is, without all the math, here's the half wave. It's a twin lead, so you really don't need this side. You just cut it. It floats there, but it could just be a piece of wire. And for 2 meters, 37, 38 inches, depending where you want to cut it, it's a half wave, right? 37, 38, 38 and a half, depending where you are. And then so the middle would be a dipole. So the middle impedance would be about just 65 to 70 ohms. And yeah, then you can hook on a piece of coax right angle to it and feed it. But like what we just showed, yeah, you can do that. And it works, but boy, mechanically, it's not very sound. It's not very sound. And plus, you'll always get reflections from here. And you'll always get distractions from that coax because it won't be a perfect 90 degrees. So it's not the ideal choice, although in the 1960s, you saw a lot of repeater antennas like this, and they would phase them with 4 of them, a 4-phase harness, and really cumbersome to get the gain that you wanted to. And you made this big harness with a lot of connections that get oxidized up in the hill, a lot of problems after a few years. So keep in mind, okay, here. So we don't want to do that. You could cut it right here, put a T and put a coax, it will work. It's just mechanically not a very easy thing to implement. Now, so what a J-pole does is it says, okay, if in the middle, 60 to 72 ohms or so, in the ends, that's where you radiate, right? That's what the high voltage point is. If it's high voltage, it's got to be low current because it's the same power across this whole antenna. So in the middle, it's high current, low voltage. In the ends, it's high voltage, low current. If it's high voltage, low current, that means it's a high impedance, right? Ohm's law. So how do you interface to a high impedance? Well, this ZEP thing kind of resolves that problem. You do a quarter wave stub, like what I said, a quarter wave. If you short it on one end, that's 0 ohms. At a quarter wave up, it will be an open circuit according to the Smith chart. And in this case, if you use twin lead, 15¼ inch plus 1¼ inch, that's 16.5. At about 16.5 inches, that's a quarter wave at 2 meters in the twin lead. I think a lot of you folks say, wait a moment, a quarter inch at 2 meters is about 18, 19 inches. That's an air. When you're in the twin lead, it slows down the speed of light. So it's like a real important formula we use in antenna design. C is equal to F lambda. The speed of light is equal to frequency times the wavelength. That always has to be true. So if you're at 146 megahertz or so, and you want to figure out the lambda, the wavelength of that, you have to go C is equal to F lambda. What C do you use? You don't use 3 times 10 to the 8th meters a second. That's an air. We're actually in a vacuum. In the twin lead, it's got the dielectric plastic. Nothing travels faster than the speed of light. Anything you put in front of it or in the transmission has to slow it down. It slows it down about, varies about 20%, 15 to 20%. And that's why it's, instead of 18, 19 inches, it's about 16.5 inches. You measure it out and you calculate it, and then you actually build one and you put it on a network analyzer. And what you're finding, what you're searching for is this is a short. You're looking to cut at 146 megahertz, where you measure a really high impedance. Again, you measure it with a little network analyzer. So basically what that stub does is it's actually a RF transformer. Why do I say that? Because if it's a short circuit here, short circuit's clearly 0 ohms. And if you go up a quarter wavelength, according to the Smith chart, it's a high impedance. Well, it's continuous. This whole thing is continuous, so that the 0 ohms, and it's here. And we say high impedance, actually, when you measure it, in the thousands of ohms. I mean, it's not infinity. Nothing's infinity, but in the thousands of ohms. Then you have to come to the conclusion, if this is thousands of ohms here, and this is 0 ohms here, there's got to be just about any impedance in between. And there is. About 1¼ inch up is 50 ohms. And that's when you tap it. So you transfer the 50 ohms to a high impedance, and it drives this half wave element. And then the good thing is you feed it from the bottom and you just hold it up like a vertical pole. So mechanically, it's very sound. You put it in a PVC pipe. It has no radios. It's round. If you make it all round, the wind would just blow around that. And we've seen it in a wind tunnel. We tested, well, I didn't test it. FEMA tested this in a wind tunnel. 150 mile per hour winds easily, because it's all round. If you stick it in the PVC pipe. So, okay, so that's the basic J-pole. Any questions? Because raise your hand, just ask a question. Do mostly raise your hand if you understand what I've said so far. Most of you, yeah, okay, good. I can carry on then. Okay. So, I mean, my RF class is basically, this is my RF class. The only thing we throw in is all the math. But I always describe things very conceptually first, because I think that's real engineering. You come up with it from your experience of just not even using numbers. Just, does it work? If you understand how waves work, quarter wave, half wave, impedance matching, does it make sense? If it makes sense, then sure, at some point you have to calculate all the numbers, but this is just basically the concept. Okay, so here are various implementations of it. You folks have done copper J's. I've built copper J's. I have my students build copper J's. In fact, they built this one. But by the way, the secret of getting students interested, I think, in engineering is you got to build things. Where I went to school with this Cal, we didn't build anything. All they threw was a bunch of math, physics, quantum mechanics, and a lot of people, I think a lot of good engineers dropped out after that. So I try to make it a little different at UC Santa Cruz. I try to make it fun. We build things and then analyze the math. So that's the this copper J. You'll see it. So it's vertically kind of like this. Yeah, it's sort of like this, but it's faced. And then you test them, and they have lots of fun testing antennas. They all ask, is there a job that we can do like this? Well, yeah, there are jobs like that. you can work, look at what I do. I build antennas and tune them and work on radio circuits and things like that. And it's interesting. I didn't do that much of it through all. I don't know how many engineers are in this group here, but boy, most curriculums is all we call analysis. I don't know why. It's all 80%, 90% analysis. But anyway, here's a copper J. You can build it on that principle I just described. High impedance point here, short circuit there, and then about 50 ohms, right about 1.5, 2 inches up. And then you tap it. If you add all this up, this is pretty expensive to do today. End caps, joints, a T, an elbow. Plus it gets exposed. It's totally exposed. It works. I think it's a great project to do in terms of performance. So. It will not work at UHF. Several reasons. It's at the third harmonic, like what we said. It wouldn't have a radiation pattern, very good radiation pattern, where 60, 70% of it goes in the air. Aside from that, what happens here is you're kind of limited by, this is a transmission line here, transmission line. On a twin lead, that distance is only 1/4 inch. When you do it with copper pipe, you're limited by the T here and the elbow. So the distance from center to center is about 1.5 inches. And that's a little too wide for UHF. For VHF, VHF quarter wave is about 18 inches. This is about 1.5, a tenth of that. It's okay. That's not the most ideal, transmission line to go from 0 ohms to here. You want like twin lead. That's really nice. But it will work. But at UHF, it won't. It's just too wide. Because again, UHF, you're 5 or 6 inches for quarter wave, and you're already, have 1.5 here. So it won't act as a very good transmission line at UHF. And plus, the other thing I noticed is since you got to jump across, this is almost 2 inches here. You can't afford 2 inches. When a quarter wave is 6 inches, 5 or 6 inches, you can't afford 2 inches where it's radiating all totally mismatched. So it's really not a very good approach to getting UHF, but VHF, it's okay. Again, even at VHF, you lose a little bit. A quarter wave is 18 inches, and here it's almost 2 inches. Even at VHF, it's not perfect, but I think it's workable. It's very workable because again, ours works fine. It works okay. And then here's another J-pole that's pretty popular called the Arrow. So Arrow knew about this problem I just discussed with you. If you use a 2-meter antenna at UHF, you'll get these lobes about 60 to 75% of your energy goes up into the sky. So they knew about this, and I don't know what their engineering staff is, but I certainly see their concept and what they're trying to do. So we have one of those too. We have one of these also. See, again, you got to buy all these. They're not very expensive. If things are in the thousands of dollars, yeah, it's a little too much. But $50, $60 here and there's no big deal to understand what other folks are doing. So they make a dual band J-pole here by doing this. The UHF J-pole is this part here, 6.5 inches. So here's the transmission line, and here's the half wave element. At VHF, this is the quarter wave matching, and then here's the half wave 2-meter portion. So they've kind of paralleled it, and they've kind of cleverly figured out the dimensions of where to put a single feed point here to get 50 ohms. That matches okay, not great. And does it work? Yeah, it seems to work. They seem to have engineered this fairly well. We do measure some losses because, again, there's one feed point. Again, it takes VHF and UHF. So the UHF portion of the antenna is here. So if you feed a UHF signal, the energy goes into here, and here's the matching network. Here's the half-wave radiator. Unfortunately, at UHF, this part of the antenna, remember, this part of the antenna is VHF. You're still feeding the signal in. Remember, this still matches a third harmonic. So what happens, what we found is half the power that you put in here at UHF goes into the right antenna, but you haven't stopped it from going into the VHF antenna. Because you have to remember, the VHF antenna, it still has a low SWR. It just has whatever goes into this antenna doesn't have a very good pattern. It gives you that 4-leaf clover pattern. So in a sense, this is a half success. Half of it works pretty well. And in VHF, there's no problem with it. But in UHF, still the other half of the power goes into the wrong antenna. So is it an improvement? Yes. Is it perfect? No. And then the other antenna I go through is The Slim Jim, a lot of folks talk about Slim Jim. Hey, you know, I made a Slim Jim. One thing I notice is I tell them, it is not in the ARRL handbook, the term Slim Jim. Somehow, I guess some Jim invented it. I don't know. Oh, I know where it comes from, Slim Jim. It's something breaking in the cars, the Slim Jim they used to use. But this idea of taking a standard ribbon JPO out of twin lead and shorting the top and getting 6 dB of gain is somehow started some craze, and it's just not true. It doesn't hurt it. It doesn't help it. All the tests we've done in simulations, it's a standard 2 meter JPO. We don't see any difference or nothing major. So don't get tied into, hey, I'm going to build it this way and get 6 dB of gain. You don't. It's just standard JPO. So okay, so how do we get dual band on this? Remember, it had to be simple, had to be inexpensive, reproducible to meet those requirements. Otherwise, why do it? So what we did in the end, what I did was this. You look at it, the standard. Okay, so the standard JPO is here, and let's talk about the matching. So we kept the matching the same, 15¼ inch. We tap it at 1¼ inch. Why is that adequate? Remember, the matching was not the problem at VHF and UHF. It was the radiation pattern. That's the radiation pattern. So if you drive this quarter wave stub for VHF, the voltage looks like it's a short circuit. As you go up a quarter wave, the voltage peaks. The voltage peaks, therefore it matches this half wave element here for VHF. That's a pretty good match. What's happening at UHF? At UHF, it goes a quarter wave, it peaks here. So the voltage peaks right about here. That's okay. If you go another half wavelength around the Smith chart, another half wave, another half here, another half there, you come back out here. Also high voltage. You also, which means the high impedance point. It's just that this here, from here to here, is another loop around the Smith chart. You come back to the same spot, which means the impedance matching is fine. You've just added a half wavelength. So the stub is fine. The stub is fine for VHF and UHF. We leave it at that. So when it gets to this point, what is it that it wants to do? Well, at UHF, it would like to see half wave, about 11 to 12 inches, depending where what frequency you want. 11, let's say 11¼ I think in our case, we just put it at 11¼ It depends where you want to go. Longer lowers the frequency, shorter raise the frequency. But here's the basic half wavelength at UHF. If you cut this out, just leave it like that, it'll work fine at UHF. But how about at VHF? Well, what we do is you put that, remember I was telling you about that quarter wave stub? If you short a quarter wave stub, at UHF, 4¼ 5 inches there, about 4½ inches there, it depends on the material. You will read on your network analyzer and open, because that's going a quarter wavelength at UHF. So therefore, if you make the stub here, if you short it there, as far as the antenna is concerned, at UHF, if you do the stub just right, it's an open circuit, which means it stops the current from continuing. Because what causes those lobes at UHF is the current continues. Okay, it sees a high impedance here, it continues, but it doesn't stop there. It's not, if it were to continue, that's not a high impedance point. It continues, the current continues going up because it's not a high impedance. So what happens? It pulls the wave up, right? If the currents continue, it's going to make, that's what makes those lobes come up, because the current continues. It's not matched, but it's current continues. You don't want to do that, because it'll make those lobes. So you use that to trap it out, right? It's a transmission line trap as opposed to an LC circuit. Well, could you have put an LC circuit there? You probably could have. But if you guys are RF engineers, you can't make good high power LC circuits at UHF. It's just very difficult, because if you characterize a capacitor, if you characterize an inductor, it's got resistive elements in it, it's got loss. It's not like trying, I mean, if you guys have tried to make traps at HF, they're hard enough. Multiply that frequency by 15 or so and try to make one. It's almost impossible. So you don't see traps very often. Get it very carefully done. So what happens at VHF? At VHF, again, that's a short circuit, and a quarter wave, after about 16.5 inches, voila, it's got high impedance point, the voltage is peaked. It's also high impedance here. That stub is no longer resonant. It only resonates at UHF. It looks almost like a wire at VHF. So then it sees this whole entire at VHF and sees it from here all the way to there. If you add up 17, 40, 4 and 1/4 and 11 1/4, it's going to be like 37, 38 inches. And there's your halfway. That's the trick. Pretty simple, huh? You wouldn't think you could sell 30,000 of these with a trick, but it works. If you line it all up, if you buy the right materials that are consistent, you buy low loss twin lead, and we special order all our twin lead from Seminole Wiring. And if you do it correctly, a good network analyzer, it works. And you deliver, thousands of these things. Let's see. So here's like the roll-up version of it. This one of my students says, oh, we can do a roll-up version of it because I can pack it on a little bag and take it backpacking and just hang it on a branch. So we did this, and we take the twin lead, but we cut little notches so it still holds, and then we put heat shrinkable tubing over it so it still holds into one piece, and we put the stub in there, put the little notch in there, and it seems to work fine. We put an RG174 cable with a BNC adapter at the end, and this works good, fine. Now the first thing you notice, the dimensions. You notice this is 18 inches, 16 1/4. Then when it goes into PVC pipe, right? This antenna goes into a PVC pipe because it's a base station. The other one just hangs in air. The PVC pipe slows down the speed of light. Therefore, its velocity factor is less than 1. Therefore, it goes into the PVC pipe. C is equal to F lambda. The speed of light is slowed down. The antenna has to be shorter. So the most obvious is instead of 18 inches, this is 17. The other one, this is 16 1/4. It's 15 1/4, and that's a good starting point. See, so this one's about 2 inches longer when it operates in air. So I'll show you one of these. I must have it. Hang on. What happened here? So this is this portable roll-up you just put in your backpack or your emergency kit. And it just comes off like this. And it's all in one piece. You probably don't see it. We kind of hide it really, really well. The stub is hidden in this heat shrinkable tubing. And then we terminate it in a BNC male. And you say, well, BNC male, mine is SMA. So what we do include in this kit, here, I'll show you the kit. Here, the kit has the antenna, but we include adapters for BNC to SMA male and SMA female. And then we also include an extension cable, which we have custom made. It's a male BNC with a female. So you can extend that, put that in there and you extend it 6 feet, or buy another one, extend it 12 feet. So that was pretty clever. I didn't think of all this stuff. Some of my students think of this stuff. They say, why don't you do this? Why don't you do this? I tried and we do it. So it is about 2 inches longer because the other antenna goes in a PVC pipe. And it looks like, right? It looks like, I'll show you one. There you go. Yeah, it goes into a PVC pipe. So again, it gets got to be a little bit shorter. And we have this PVC pipe here, and this is the same antenna. It just, we stick it in like this. And then the end looks like that. And then you would just hold it up. You would just mount it somewhere like this. Again, it doesn't torque. So let's see. So what you can see here is the results. This is on our HP 8591 spectrum analyzer. And sure enough, when we use the 2-meter J-pole at UHF, it gives this result, which is about a 6 dB loss. But if we use our antenna, with that modified stub, you get about 6 or 7 dB of gain. So you don't lose it. And if you actually measure it, which we do, this is an interesting exercise we did. To measure antenna performance, the general rule we use is you got to measure it on 3 different days: a rainy day, a foggy day, and a sunny day, because they'll all give these slightly different readings. Because again, the velocity factor changes, right? On a rainy day, obviously the speed of light slows down because there's more moisture in the air. So it's the same thing with a foggy day. And a dry, sunny day, the speed of light is actually faster. And you can actually, there's ways to measure that. You will see it. So we take 3 different days and 5 different measurements. And this is the results. When you take all those averages, they come very close to theoretical, extremely close. And you expect that after 15 measurements. So quarter wave mobile is minus 27.7, just reference. This is just, by the way, a typical day in a parking lot, 50 yards out. And then we kind of compare it to like a rubber duck. Yeah, sure enough, rubber duck gives about 6 dB of loss, minus 30. A VHF J-pole is a little bit better, right? Minus 24.7, it's minus 23.34, about 1.4 dB better on average. It's supposed to be like 1.6, 1.7, but our actual measurement is about 1.4. It is definitely better. So if you ever get a chance to measure a J-pole with a ground plane, you should see it is better. Not night and day, but on a weak signal, and you switch between the two, the J-pole will be better. And then our J-pole at this is at VHF is pretty good, minus 23.47, very close to that of a standard VHF J-pole, maybe losing 0.1 dB because of that little stub, but yeah, that's insignificant. And that's not measurement error, I don't believe. That after 15 measurements, yes, you do lose about 0.1 dB. Now, how about at UHF? At UHF, that's the one we want to cure. UHF, do we still lose that 6 dB? Well, we look at it here. At UHF, again, same test equipment. The signal strengths are a little bit different. The UHF measures 38.8 dB quarter wave ground plane. Rubber duck, the UHF doesn't lose much. I mean, 3 dB, 2 to 3 dBs. And in fact, if you choose a really good one, if your handy talk's got good ground, you probably can get it to no dBs or close to it. But it'll lose a few. But a rubber duck at UHF works pretty well because it's close to a quarter wave. And compared to at VHF, well, VHF, the quarter wave is 18 inches, and a rubber duck is 5 or 6 inches, so you lose quite a bit of dBs. So it's not good to use a rubber duck at VHF, but at UHF, it's acceptable. It's not bad. Now, a standard J-pole at UHF is terrible. Again, you lose about 6 dB, right? Minus 38, you're down minus 45. That's a lot. 75% of your energy is going into the sky. And sure enough, when we use ours, hey, it almost comes all back. Instead of minus 38.8, it's minus 38.9, 90%, 95% back. That's not bad. It does the concept work. Obviously, we can't do it perfect, but it's night and day, compared to minus 6 dB. It's now only like minus 0.1 dB. So the concept really does work, and it's pretty simple. We think it's, you can duplicate it with some patience. You can duplicate it somewhere else. Just follow our directions, and it does work. Let's see. So this is our lab from 10 years ago. I got to get a picture of our new lab with our new. This is our 8753 we used for 20 years. We just got a new 5062, new super color, and pretty nice unit. In fact, I have it. It's just in the other room right now. So I've got to take a new picture of that. Okay, so the other question that comes up often, Pop, that stub, that's what you've added. How good is that stub? Well, with RG174, at 445 megahertz, remember, it should be way out there at infinity. It's not infinity, a couple of K, that's all it is. So maybe that's that little losses we're getting, 0.1 dB or so. It's very hard to get infinity. Not the stuff very close to it. But it's certainly closer to infinity than it is to 50 ohms and 0. So it does help. It does, in general, works, but nothing's perfect. There's no perfect opens and perfect shorts at UHF and above. So I swept this. This is all swept from 30 megahertz to 1 gig. That's all this stuff. So 1 gig. So this is low frequency here, goes all the way up here, and at 445 it hits here, and then at 1 gig it hits about there. And it's pretty stable too. I put my hand around the whole thing, so everything that's going to vary because it's not resonating. But At 445, it stays, not infinity, but not bad. I mean, if you ever work in an RF lab, that isn't bad. It's acceptable. By the way, if you do that with RG8X, it's even better. We do it with RG174 because it's just convenient and it makes the antenna fairly light. We do make a higher power version, the 250 watt version, which we do use RG8X, and then it's much better. It's much closer to there. Then people ask them, how about at 146 megahertz? Well, at 146 megahertz, that looks like a piece of wire, an open circuit wire, that stub, and then an open circuit wire looks like that. So yeah, close enough. Yeah, it might have some losses, but boy, it's close enough. It looks like a piece of close to a piece of wire at 145 megahertz. So see, here's the mounting. See, if you look at this, if you're a mechanical engineer, to hold this antenna up vertically like this takes up much less force or torque at that point than if you had made this thing vertical. If this is halfway sticking out, the torque that you would have to hold, and over time on a hill and a windy hill, it would just tear apart. This is very difficult to tear apart. Again, it's all round too, so wind just kind of blows around it. And the disadvantage here, of course, is it is a half wave and a quarter wave matching. So it's a 3/4 wave tall. Well, a ground plane is only quarter wave with 4/4 wave or 3/4 wave radios. So it is tall, but again, you've designed it correctly so the wind load is fairly low. Let's see what's the next slide here. So here's our roll-up version. Great for backpacking. Great if you're in an apartment. It's the same concept. You just hang it up, and then you can buy extra extension cables for $5. We also include, if you want a BNC to PL259 to interface to your mobile radio. Okay, so we have other talks. This is the end of it. This is a talk on how do you get gain. That's another hour talk. How to get gain out of a vertical J-pole. And of course, our triband talk here. How do we get the third band out of it? All the little problems we have on it. And then, I just kind of talk about radios. We don't sell these radios. I just want to encourage people, hey, 220. If you're wondering about 220, hey, 220 is cheap, man. You get these B-Tech radios, $128. They cover 2 meters, 220 for 40. Radio Oddity sells it for like $100, 25-watt mobile. Of course, this popular B-Tech, the ×3 is the triband version. It's a UV 5x3. Now I've got some of those. They work fine. Not very expensive. In fact, during the holidays, I picked 3 of these up for raffle prizes for $22. Some guy was selling for 22, and they work fine. So if you're hesitant about getting on 220, try one of these. In fact, let me see a show of hands. How many of you guys have one of these? None. Hey, they're cheap, man. Oh, you do? Okay, I see a few hands. Yeah. I mean, they work pretty well. They work. And then if you get it stolen, it's not a big deal. Icons, the Icon triband mobiles are really expensive to begin with, but these are pretty inexpensive and they get the job done. I don't like to run them on high power. They run pretty hot at 25, but I'm driving around the city at 10 watts is fine. 10 watts on a good mobile antenna is fine. Here's something we do sell. We had a contract with the university with CountyCom back in 2012. We had they wanted us to design. It was a regular AM radio, but they wanted us to put single sideband on it, and so we did the software for single sideband. They had a government contract to do this, and then what do? They give it to us. So we didn't charge them. It was just, I don't know how many of you guys are engineers, but to detect single sideband is fairly easy. It's just a product detector, right? You need an oscillator to remix it to big baseband. It's actually almost sometimes easier to detect an AM single sideband. So we were responsible to get the upper sideband, lower sideband detections, assessing CW. It's got a 22-bit DSP, very accurate frequency, very accurate. Actually it even covers down to 150 kilohertz, the beacon bands, and it has stereo. Anyway, if you ever go to the CountyCom site, these go for, with postage and everything, about a little over $100 if you have to pay the California tax. So if you guys want one, we've got a bunch of them for $65, which we can just ship it with the shipment we get you guys. So it's a good $35 off. We'll be glad to send you one. We've got a box left. And I sell these at Pacificon. I usually bring a few, and they usually all sell out. Really, I mean, it's a great radio. When we designed this, it was really quite an effort. It does not take a big antenna. I matched it to a magnetic antenna. So you just pull out the antenna, get out in the clear, and you can hear 40 meters, 20 meters, quite well. Okay, any questions? How about questions? I'm welcome to questions.
All right, thank you. All right, thank you. Any questions?
So,
Kent?
yeah, I've got the, one of your antennas, but my question is about these Nagoya things you put on like for handhelds. How do those stack up, you think, with your DB, you know, the kind of extended antennas? Yes, could you pass me-
Okay, I think I heard the question, right? How does like a Nagoya 777 stack up?
Yeah.
Oh, yeah, you have to turn off the audio. Well, we did a whole luncheon about 2 years ago here, testing with my one of our ham meetings here, because I have a luncheon in my house, and we run circles around. You gotta have the Nagoya. You gotta have the other quarter wave to resonate against. Otherwise, it's very hard to do. The Nagoya is an okay antenna, you know, for a whip, it's okay, but we have all the data on it. Our antenna just ran circles because it's a true half wave, of course. So it resonates. Because you ever put a Nagoya without radials on an SWR analyzer? Okay, I don't hear your audio.
Go ahead. I'm sorry.
Yeah, so yeah, turn down the audio, the volume, and then repeat the question close to the computer. Jim, you can just repeat the question.
Okay.
So
So what was the next question?
I was wondering if it would be possible for Ed to make his kind of J-pole, but for 6 meters.
Can you make one 6 meters?
you can, but if you calculate the dimensions, okay, I'll tell you several reasons why we don't. If you calculate the dimensions, obviously it's 3 times taller. We're already about 60 inches. So it'll be about 180 inches. Be quite tall. Probably the other reason why we don't do it because most of our business making these antennas are commercial. There would be no commercial market down there. It would be all ham. We could, but I guess we don't. It's again 180 inches. It's let's see, that's 17 to 18 feet.
Do we have any more questions?
Yeah, Jim, he says that in his information not to glue it because
You tell us not to glue the PVC.
Oh, okay, good. You know why we do this? Very good reason. Some people glue it, even though I tell them, do not glue, just hand tighten. You can put a little silicone rubber on it, make sure you can remove it. In every case, not very many, probably 4 or 5 cases that I've seen, people thought it was the antenna after 2 or 3 years. Something's not working. We think it's your antenna. I go, well, go take it down. I take it. I said, well, go pull out the cap. Maybe something wrong. Oh, I glued it. Well, then you got no other choice but to saw it at that point. Now, put silicone rubber. It's okay because you can always rub that out, but don't ever glue it. You end up sawing it. And when you think about when you saw it, it's pretty hard to connect back up. And in every case, it's usually the coax, right? The way you can test the antenna very quickly is if it's a DC short, from the SO239 connector, it's probably okay. But if you don't glue it, you just pull it out on a table and you can see whether it's working or not. But you glue it, then the only test instrument you have is your antenna analyzer, or else if it's a DC short or not, because it's a DC shorted antenna. That's why we don't glue it. But I tell people, if you want to put some RTV rubber around it, that's fine. You don't have to put it at the top because the water always runs down. But the bottom, possibly, yes. But all that, like RTV, something you can rub off.
Do we have any more questions?
Yeah, so let me, after question, so here's how we raise funds for our group. People say, boy, Ed, are you a nice guy or what? Friday nights, you're talking to, no, I'm not that nice, okay? I'm not that nice. I have to raise funds for my group. My group, we do build the antennas. I do tune every single one and make sure everyone works before it leaves here. But I don't cut all the wire and draw the holes. That's how these guys make a living going through school. And we support between 2 to 3 students a year, room, board, and everything. I mean, basically, they're working for me. We don't do it at the university because then I got to give them 15%. So I said, no, you come over to my house and do it on your own. And they work about 10 hours a week. It's enough to put them to school. But the way we raise funds is, so we make the DBJ-1, that's the ham version. So if you buy through the club, it's $32. We normally sell this $40 on our website and then $44 on eBay. So you'd save about $8, and plus we'll do bulk postage, you wouldn't have to pay the postage. And we do this also in commercial, 152 to 157, which also covers the GMRS band for 460, 470. The roll up, again, we normally sell it for 40 on our website, 44 on eBay, it's 32 here. Our triband normally is about $83 of postage, $83 of postage now. If you go through the club here, one time only through the club now, 65. That's a triband that comes with the PVC pipe. We ship it with the pipe. And then some accessories if you want extra extensions with the rope, that's $5. And then of course with the DBJ-2, we don't always include the BNC to PL259 connector because a lot of people don't need it. If you need it, it's $250. And then of course the software-defined radio, which is really cool. If you guys are, show of hands, how many of you guys have one of these? The GP5, anyone? None? It's a really cool radio. It'll tune single sideband, lower sideband, upper sideband, right on the money. And I designed it with a magnetic antenna, so it doesn't not need a resonant antenna because it's not transmitting. The whip alone, just standing outside, works absolutely fine. So that's a project we worked on. It's been very successful. CountyCom delivers a lot of these to the government for about $100 each. So that's how we raise funds. I try to be a nice guy, but I do these because we do have to support my group. We used to depend on some grants here and there, but no longer. They were just unreliable.
So ask where that website is.
Where's the website where this is?
Just type in your search engine, Ed's Antennas.
Okay.
EDSANTENNAS, and you'll get there. On any of the browsers, it'll come up.
I don't know if you saw, but here's one of your antennas right here.
Yeah, I saw that. Who owns that one?
Me.
Oh, you. Okay. Does it work?
Oh yeah, I tried it for the first time yesterday.
Okay. Oh, good.
I went to Lowe's and I've got like 4 lengths of this stuff. But
No, you have the tri-band or do you have the dual band?
Dual band.
It's a dual band.
Yeah, and I was running 50 watts to it.
Yeah, it should work fine.
You remember the Miracle antenna, Miracle Whip, Miracle Ducker? That's what I was using before, and it has the maximum of like 20 watts. That I feel.
Oh, really? Okay.
And that was indoors. I had this indoors next door in another room to prevent interference, and I was running 50 watts, and that seemed to work fine. Not getting.
They work pretty well.
Now I'm going to put it outside like it should be on.
Oh, it should work great. It should work great outside.
Yeah.
Yeah, so that I really ask you to donate to my group because we support about 3 students right now. And with COVID, things have been pretty tough on them. I tell you, if you have to teach under COVID, this is what I tell people. I could not, I had some new students. I've never met them live. It was all on Zoom. I swear, I would not be able to recognize their face if I met them on the street. Because even though they don't have masks, I don't know their height, their weight, right? And I hate to be a racist. Most of my students are Asian or Indian, and I'm Asian. Hey, it's hard to recognize. I mean, that's how bad it's been. And I think they've really suffered in terms of learning. It's been pretty bad. I really had to water down my class. I just can't get the concepts over. So I've had 3 of them come over and work with me. The ones I work with, I can recognize, but a lot of them just take the class. It's been really sad. And the school has not reduced their tuition one bit. And I was telling people, it's interesting. They're getting a master's virtually online. Isn't that pretty scary? And they go, well, not as scary as that surgeon MD that's getting it online. Well, that's true. So, but the good news is, every one of my students has a network analyzer that can do assignments. So the tools have gotten better, but I just don't know. I mean, luckily we're ending this fall. We're going back for sure. That we're no buts, no ifs. We're doing live again. We have to. But anyway, hey, if there's no more questions, thanks a lot for your time and have a good evening.
Your time. We really appreciate you joining us.
Try to help us out. Jim, I'll give you a spreadsheet, and then you can kind of send out the spreadsheet to the members, and you can check it. Again, it's a very good price with the talk because $8 off from our website, and it's $12 off from the eBay price. So it's quite pretty good discount.
All right, email that to me and I'll send it.
I will. And thanks a lot. Hey, thanks a lot for your attention. And I'm gonna go get some dinner. It's cooled off, man. Hey, what temperature is it out there now?
It's over 100.
Yeah,
Still?
it's over 100 out here.
Right now, even?
Yeah.
Oh my God. Oh, that's too much.
This is cheap.
At least it's 80 here now.
Yeah, I know. Sunnyvale's nice.
Hey, it was pretty hot this afternoon. I really seriously got to think about getting air conditioning here. I mean, global warming. You don't, year by year, you say, well, it's a quirk. No, I've been here for 40 years now. Slowly, it's gotten a little hotter. In June, I mean, this is unheard of in June 40 years ago. Maybe September, August, remember it used to get hot, Indian summer. But in June, this is pretty hot for June. Let me tell you, that's pretty hot. And I can't wait until what's going to happen in August of this year. That kind of worries me. And you guys, your fires, right? You guys worry about your fires.
Yeah, we had one
We had
yesterday.
one today.
Whoa. Well, get your two-way radios ready and hope for the best. Hey, you guys have a good evening. You guys take care.
Thank you very much.
You're very welcome. Let's see. How do I get out of here? Ta-da. There you go. Now I can see all you guys. We'll see you later. Hey, take care. Thanks a lot for inviting me.
Okay.
Careful of those fires.
Yeah.